All right, some announcements for you all. Tomorrow, my office hour is in my office at 2 p.m. And then Friday, we have recitation at 8. And then Friday in class is our unit exam 2. All of this is in the Blackboard announcement from this morning, by the way. So unit exam 2 covers sections 14.4 to 16.2. There are 18 multiple choice questions, 2 short answer questions, and I've not done this before, but I'm going to tell you what those questions are focused on. So one of them is an ICE table, but it's an ICE table where you won't need the quadratic formula. I think that will end up taking too much time. So yes, that's one question. The other one is you have some reactions that you need to manipulate, combine, reverse, whatever, with their K values to then get the K for an overall reaction. So both of those are from chapter 15. At least that's when we did practice. So you can use that to guide your studying, but remember that's the 2 short answer questions, so that will be 12 of the 60 points. Each short answer is 6 points. So then just make sure you bring a pencil or whatever you want to write with in a non-graphing calculator. You are not filling out a Scantron, so you don't need a specific utensil. And then I'll provide the equation sheet as usual. And then there is an Achieve homework that is posted due on Monday. The first 3 questions are relevant for unit exam 2, and then the rest of them are from content after 16.2, so the rest of what we covered Monday and what we'll get to today, so you can save that for after the exam if you want to. And then the chapter 15 adaptive quiz is also available. That is due this coming Monday, same time as the Achieve homework if you want that extra credit point toward this assessment. It'll either go towards this or the final, whichever grade is lower. Questions on any of this? Okay. We will start by reviewing the learning check, which was the learning checks, which were review from chapter 12. So we did this at the end of class. These slides I think are in your chapter 12 PowerPoint, but I'll just go through them briefly here. So remember, we really have 4 types of intermolecular forces, but the one that's not on the slide is the ion dipole forces. Those are between an ion and a molecule that has a dipole, like when you dissolve sodium chloride in solution. And all of these questions, we don't have any ions. So the strongest force of these 3 is hydrogen bonding, and then dipole-dipole is slightly weaker, and dispersion forces are the weakest. Remember, hydrogen bonding forces occur when you have a hydrogen bonded to fluorine, oxygen, or nitrogen. In this molecule, there is an OH bond right there, so that meets the criteria for hydrogen bonding, so that would be the strongest in this molecule. In the next example, we have F2. So you all should be able to draw these Lewis structures at this point as well. But here's the F2 Lewis structure. 2 fluorine molecules, each with equal electronegativities. There's no polarity in this. Well, for one, we don't have a hydrogen, so it can't have hydrogen bonding forces. For dipole-dipole forces to be present, we need to have a polar bond. That molecule must have a polar bond. If we have 2 fluorines bonded to each other, that's the only bond. They have equal electronegativities. That is not a polar bond. So there's no dipole-dipole forces, so this one is dispersion, which are forces between nonpolar molecules. Next, we have CH2F2. So we need to draw the Lewis structure to be able to answer this question. Remember that chlorine likes to make 4 bonds, hydrogen only makes 1, and fluorine only makes 1. So that means that our carbon atom, which makes the greatest number of bonds, would be in the center, and then is bonded to 2 hydrogens and 2 fluorines. If you go through the process where I'm skipping through like the process of drawing the Lewis structure, but you add up valence electrons, put the atom that makes the greatest number of bonds in the center, arrange everything else around, add lone pairs to outer atoms, and then add to the central if you need to. But this is the final Lewis structure. In this molecule, we have two polar bonds. The carbon to fluorine bonds are polar. The carbon to hydrogen bonds are basically nonpolar and definitely not as polar as the carbon to fluorine bond. So this molecule has polar bonds. It has overall molecular polarity towards the area with fluorines. So there is a dipole. We have dipole-dipole forces. It is not hydrogen bonding because the hydrogen is not bonded to the fluorine. It's bonded to a carbon. So it cannot have hydrogen bonding forces. Then the last example, we have BCl3 boron in the center, bonded to 3 chlorines. Again, if you went through the full process of drawing the Lewis structure, you should get this Lewis structure. Here we have polar bonds, but now in this molecule, we have all equal bonds to that central atom and no lone pairs on that central atom. This is an overall nonpolar molecule. So the only time you'll have polar bonds but a nonpolar molecule is if, for one, that central atom does not have any lone pairs, and two, all bonds to that central atom are equal. The same atom is on the other side of that bond. So that's the case here. All bonds are equal, no lone pairs on that central atom. So this has no net polarity in the molecule, which means the strongest force is dispersion forces. Okay. Questions on any of these? Yeah.
Why would you do it?
Because I had those iClicker questions on Monday. That's all. No. But it will be on the final. Other questions? Okay, also this polarity will be relevant when we discuss acid trends. So what makes one molecule more acidic than another. But that's not until after unit exam 2. So this is where we ended class on Monday. We talked about calculating pH of solutions. Neutral solution would have a pH of 7. That's when OH concentration, OH minus, is equal to H3O plus. pH less than 7 means there is more H3O plus present, and so that's an acidic solution. pH greater than 7, there's more OH present, and that's a basic solution. Okay, so with that in mind, and you might look back to our equation for pH on the slide, pH right here. We will start with this question. Determine the pH of this solution and then classify as acidic, basic, or neutral. So once you know the pH, you should know if it's acidic, basic, or neutral. So we have 7.2 times 10 to the negative second molar HCl. To find pH, we need concentration of H+. So think about what you know about HCl, determine concentration of H+, and then calculate pH. I'll give you all a few minutes to work on it before we talk about it together. All right, let's review this. It seems we've diverted our conversation. So, oops. Okay, so HCl, when you see HCl, I want you to think this is a strong acid. It fully ionizes. So we have our list of strong acids, HCl, HBr, HI, those hydrogens bonded to halogens, but not fluorine. Those are strong acids. If you have 7.2 times 10 to the negative second molar HCl, that fully ionizes into H plus and Cl minus. So the concentration of HCl is the concentration of H plus solution. We can do that calculation where we start with 7.2 moles of HCl over 1 liter of solution. And then with this equation across the top, for every 1 mole of HCl, we have 1 mole of H plus. So moles of H plus per liter is equivalent 7.2 times 10 to the negative second moles of H plus per liter. We can only do this directly because this is a strong acid. We're going to talk about weak acids later today, and these are less straightforward. Weak acids don't fully ionize, so you can't directly calculate concentration of H plus like we did here. But strong acids, you can do that. Strong bases, you can do that. So here we have concentration of H plus. Now we can calculate pH, which is negative log of the concentration of H plus. And I get, I think it was 1.14. Did you all get that? Okay. I don't have it written down, but we got that earlier today. So pH of 1.14, is this acidic or basic solution? Acidic. Less than 7, acidic. Yeah. So, as in, what's the point of doing this? So this is helpful in situations where you, for one, I'm just showing that we can do the calculation, you get the same thing. But also, if you have, for example, a strong base, it's not a one-to-one. The concentration of this will not equal the concentration of OH minus. Concentration of OH minus will be double the concentration of this. So that works. It's a one-to-one because all of the coefficients are 1 up here. But if they're not all 1, then you just want to make sure you keep that in mind. Okay, so we talked about pH, how to calculate pH. We can also calculate pOH, which is analogous to pH, but we just take the negative log of the concentration of OH minus. So now we're thinking about the base. And sometimes this is useful if you know more information about the base, but you still want to calculate pH, which we will do in the next question. But remember that for any solution in water, the concentration of H3O plus times the concentration of OH minus is Kw, 1 times 10 to the negative 14. So if you take the negative log of both sides and simplify, the pH plus pOH is equal to 14 for any solution. So if you know one, pH or pOH, you can find the other because the sum of them should be 14. And they are complementary to each other. So if you have a neutral solution, the pH, which is shown down here, pOH is up here. If pH is 7, pOH is 7. Add them together, you get 14. If you have slightly more acidic, so lower pH, then you'll have a slightly higher pOH. So 6 for slightly more acidic pH, and then 8 for the pOH. But if you add them together, you'll always get 14. So now with that in mind, try working on this problem where you're calculating the pH of a solution. knowing that is 6.9 times 10 to the negative second molar sodium hydroxide. Keep in mind sodium hydroxide is a strong base. All right, there is more than one way to solve this. I'm going to show you two ways. One is much more straightforward, and I'll do that one first. And the other one, it still works, and we're using things that we already know to solve it. So either one is fine. I'm not going to care which one you use. But all right, so we know sodium hydroxide, strong base, fully dissociates into Na plus and OH minus, all in a 1:1:1 ratio. So the concentration of OH minus, so here I'm skipping that conversion, concentration of OH minus is 6.9 times 10 to the negative second molar. So with that information, there are two things that you can do. First one, which we'll do on the left side here, is directly calculate POH. POH is negative log of this concentration. POH is 1.16. Now, with a low POH, that indicates the solution is basic. If the POH is low, then the pH must be high. High pH also means basic. So we calculate POH, but that's not what we're looking for. We're looking for pH. From the previous slide, we know that pH is 14 minus POH. So the pH is 12.84. So using POH, or using concentration of OH, we calculate POH, use the pH plus POH relationship to find pH. Okay, so that's one method. Other method is using the KW relationship to first calculate H3O plus concentration, and then with that directly calculate pH. So we won't calculate POH with this other method. So remember that KW is H3O plus concentration times OH minus concentration, and this is equal to 1.0 times 10 to the negative 14. So H3O plus concentration is Kw divided by OH minus concentration, which in this problem is 6.9 times 10 to the negative 2. So concentration of H3O plus, simplifying that fraction, is 1.45 times 10 to the negative 13 molar. So now that we have H3O plus concentration, we can directly calculate pH. Negative log of H3O plus which is 12.84. I said I don't care. It doesn't matter. There are some problems where this method will be more useful. For example, what we did earlier, so the section on the auto-ionization of water, if all you're looking for is this concentration, then this method is more direct to find this concentration, but either one is fine. You get the same answer either way. They're just using this relationship, so Kw being 1 times 10 to the negative 14. That's why POH plus POH is 14. So we're using the same property of the solution, but in different ways. So that's why it doesn't matter. Okay, now I hear that you all have used pH indicators in lab. And if you know information about the concentration of an acid or a base, then you can calculate pH, and that will give you information about the acidity. But there are cases where you don't know the exact concentration of the acid, or you're looking to find the concentration, or you have a solution, you don't know if it's acidic or basic. That's when we will use indicators. So an indicator is a soluble colored dye that will change color depending on the pH. So the indicator itself is a weak acid or base, and it reacts with the acid or base in the solution and causes a color change. So litmus paper, this is a common indicator to determine if solution is basic or acidic. So what I have here, there is a paper to determine if the solution is acidic, a paper to determine if it's basic, and all it does is change color, pink or purple, or blue maybe, I can't really tell if that's blue, but either way, it changes color, and that just tells you if it's acidic or basic, if pH is greater than 7 or less than 7. But it wouldn't tell you if it's 8, 9, 10, 11, 12, or it can't give you that specificity. Universal indicator dye has more ranges of color that will give you more information about the pH. So these are screenshots from a video in the book. You could watch someone actually do this experiment. But they have sodium hydroxide, which is one of our strong bases, ammonia, which is a weak base, baking soda, another weak base, distilled water, which should be neutral, vinegar, slightly acidic, hydrochloric acid, strong acid. Then they add a universal indicator to all of these test tubes, and you can see the different colors based on the pH of those solutions. So different color will be associated with a different pH. Then sometimes, and I think we might have this in lab, where you will have basically the universal indicator but on a strip, and that can also tell you about the acidity using a piece of paper rather than adding the dye to your solution. So these are ways to determine the pH of a solution. But also there is limit to how much detail this can provide. Like the dark purple might be like 12 to 14, but it's still not telling you anywhere within that range. So there's specific ranges for the dye. Another instrument is a pH meter, and this is an electronic device that is used to measure the pH of a solution. The pH meter has a probe that you can put into some solution, and then it will provide a readout of the pH. This readout is 6.70. So it is precise up to those 2 decimal places, which gives you much more specific information about the pH of that solution. So different ways to determine pH if you don't know concentration. All right, let's go to next section here. So far we've talked all about strong acids and bases, which makes our problems easier because we know that they fully ionize. When we're looking at weak acids and bases, we have to think about what happens when that solution reaches equilibrium, and then we'll use some other information to describe these solutions. So strong acid on the left, HNO3 is one of the strong acids. It fully ionizes in water. So if you know HNO3 concentration, you know once that solution's added, or once that acid is added to solution, that's also the concentration of H+, that's also the concentration of NO3- because it fully ionizes. So those like the problems that we already did. Over here we have a weak acid. So HF is a weak acid. It does not fully ionize in water. Most acids are weak acids, or most bases are weak bases. We have a very finite list of strong acids. So as a weak acid, it doesn't fully ionize, which means we don't know if you add 1 molar HF to solution, you do not get 1 molar H+. Some of that HF that's added to solution remains as a full compound. It does not separate into the ions. So this is an equilibrium reaction. It has an equilibrium constant expression. For an acid, we're looking at an acid added to solution. Sometimes we use Ka. So that A subscript is for acid. We'll talk about Kb for bases. It's the same thing as K. Concentration of products. Over concentration of reactants, leaving out water because it is a liquid. Since water as a liquid is not included in the K expression, altering the amount of water doesn't influence the equilibrium position. It's not going to cause the reaction to shift right or left because it's not part of K. So that goes back to Le Chatelier's principle. Equilibrium does not depend on liquids or solids, so if you alter either one of those, the amount of either one, you take some away or add some more, it doesn't alter the equilibrium position at all. All right, so let's talk a little bit more about Ka. For a weak acid, you can write the ionization reaction as just the weak acid forming H+ and A-, or we did the same thing with strong acids. Have the acid with water that form H3O+ and A-. So for any weak acid, the Ka is H+ times A- over Ha, or H3O+ A- over Ha. The only difference between these is if we're using H3O+ or H+, but remember they're interchangeable in our class, so either one it works. I do want to be more specific about what we mean by HA and A minus. For any acid-base reaction where a proton is transferred between the acid and the base, we always have an acid, a base, a conjugate acid, and a conjugate base. So HA is the equilibrium concentration of the weak acid. So we're just saying for any weak acid, if it's an acid doing a proton transfer reaction, it must have a hydrogen that it's transferring. The rest of the molecule we're just representing by A. So that could be a fluorine, it could be the rest of acetic acid, which is 2 carbons and two oxygens, a couple of hydrogens. Just generally, this is the weak acid. And so if this is the acid, looking at the expression on the right where we have acid and base, then on the right side, H3O plus is the conjugate acid, and A minus is the conjugate base. So A minus is the conjugate base of the weak acid. So A minus in brackets, that's the equilibrium concentration of the conjugate base. And then concentration of H plus or H3O plus is equilibrium concentration of the conjugate acid. So the hydrogen ion or the hydronium ion. A little bit more about Kb and then we'll do a question. So for a base, a weak base in solution, we have base B reacting with H2O. Definition of a base is that it accepts a proton, so H2O gives away a proton and becomes OH minus, B becomes BH plus. So Kb BH plus times OH minus over concentration of B. Again, we exclude H2O because it does not matter for this expression. Okay, so when you're ready, go to the next slide. Ammonia, NH3, is a weak base. So the equilibrium reaction has been started for you, but draw the products of the equilibrium reaction and then write out the equilibrium constant expression, the K, for NH3. Okay, so to think about what these products should be, the conjugate acid and the conjugate base. This statement that NH3 is a weak base is what indicates what's giving up a proton and what's accepting a proton. So if NH3 is the base, remember that bases accept H+, which we call a proton. So the base, the NH3, is going to accept an H+ from H2O. So it will become, now NH4, it has one more hydrogen and it gained a +1 charge. H2O gave away an H+, so now it is OH with a minus charge. So here we have NH3 is the base, H2O is the acid, NH4+ is the conjugate acid, and OH- is the conjugate base. If you're adding a base to water, you should always have OH- on the right side. And that's because if you're adding a base, H2O is the acid, it gives away a hydrogen, becomes OH-. So then the equilibrium expression, which you have a lot of practice with at this point, concentration of products over reactants. Again, leaving out water. So again, base on the bottom, conjugate base, conjugate acid on the top. Okay, so now Ka values, we haven't looked at any values for Ka yet, but weak acids dissociate just a little in solution. So most of the acid still remains as the compound, which means Kas are really small. So here are some examples. Acetic acid, here's the formula. This is the acidic component of vinegar. So it is acidic, but the Ka is still 1.8 times 10 to the negative fifth. So a pretty small number. Here's another acid with Ka 5.8 times 10 to the negative 10, even smaller. So just like the concentrations of H3O+ in solution, those can be really small, and so we use pH to have more manageable numbers. For specific acid, adding acid to water, we get a Ka value. Those Kas for weak acids are really small. So we have a better way of dealing with those, and that's the pKa, which is similar calculation. We take the negative log, but now we're taking the negative log of the Ka. Because of this, lower pKa's indicate stronger acids. If you have a large Ka, that means the acid is stronger, it's producing more ions. That will result in a low pKa. So again, pKa values describe a specific acid molecule. pH is a property of a solution that can be altered by adding acid or adding base. pKa is a property of a specific acid molecule. You'll do a lot with pKa's in the fall when you take organic chemistry. But just like pH, if you have a low pH, that means acidic solution. If you have a low pKa, that means you have a stronger acid. And we've talked about strong and weak acids. Our list of strong acids are really strong acids. Then all the other acids that we have under the umbrella of weak are not equivalent in their acidity. Some are stronger than others. So that's why we use pKa or Kas, which is related to pKa, to compare the strengths of weaker acids. And then if you know the pKa, you can calculate Ka by doing 10 to the negative pKa. So just going backwards if you know the pKa of an acid. Okay, let's round out our class today with this learning check. So we have 0.1 moles of an unknown acid. I'm just going to represent it as HA, dissolved in enough water to make a 1 liter solution. So you're adding an acid to solution. After it is added, the resulting pH is 2.20. Calculate the Ka for HA. So we're going to think about a few things here. Let's remember what Ka is. Ka, we have the equation there, the reaction equation. So Ka H3O plus concentration times A minus concentration divided by HA concentration. So we need all three of those values in order to calculate Ka. It also has to be at equilibrium if we're calculating K at all, Ka in this case. That has to describe concentrations at equilibrium. We have 1 mole of the acid dissolved in water, but not all of that 1 mole will remain as HA. Some of it dissociates into H3O plus and A minus. But this is a weak acid, so again, it's not 1-to-1. Do you see where we're going here? What we're going to need? What do we have to do for this one? You've done it in lab. We've done it before. Calculating equilibrium concentration. We know initial ice table. Yeah, we need an ice table. So with the ice table, set that up. Think about what we have. All right, so we've got the reaction equation across the top of the ice table. We have initial concentration of HA only. We have 0.1 moles added to a 1 liter solution. So molarity is 0.1 divided by 1, which is 0.1. H2O, that's a liquid. We don't care about H2O. Leave that column blank in the ice table. Don't need any information for that. We just need H3O plus and A minus. But initially, all that's added is HA. So H3O plus is 0 concentration and A minus is 0. Now, in reality, any water, even if it's pure water, has a really, really low concentration of H3O plus. If it's neutral, 1 times 10 to the negative 7. So we're approximating this as 0. So we're going to keep it as 0. But when that becomes relevant in the future, I will let you know. But we can assume 0 at this point. So if all that is added to solution is HA, some of that HA will dissociate into the conjugate acid and base. So HA concentration will decrease, H3O plus will increase, and A minus will increase as well. So we have minus for HA, and then plus X and plus X for the two products. Now there's one more piece of information here, which is the pH. What can we do with the pH to help solve this problem? What does the pH tell us? Or what does it give us information about?
Concentration
Of? Yes, concentration of H3O plus. So remember pH is negative log concentration of H3O plus, and this is equal to 2.2. So this tells us at equilibrium, there is some concentration of H3O plus that gives us a pH of 2.2. With the pH being 2.2, we can calculate H3O plus concentration by doing 10 to the negative pH. And that gives us H3O plus concentration at equilibrium. So 10 to the negative 2.2. This is 0.0063. So pH is at equilibrium. Gives us information about H3O plus concentration at equilibrium. Now we can plug that value into the ICE table. That's H3O plus concentration at equilibrium. So if we started with 0, concentration of 0, added X, and we got 0.0063, then X is equal to 0.0063. Now we can fill in concentration of A minus is 0.0063. Concentration of HA at equilibrium is 0.100 minus X, so minus 0.0063, which is 0.0937. So very similar to other ICE tables that we've done, we've got to use some other information to fill it in and then solve for X, so we have pH in this case. But now that we have equilibrium concentrations of everything involved in the equilibrium expression, we can complete the problem, which was asking us to calculate Ka. So I have the formula for Ka at the top. Here I'll just plug in values. 0.0063 for concentration of H3O plus, 0.0063 for concentration of A minus, divided by 0.0937 for concentration of HA. And then this is equal to 4.24 times 10 to the negative 4. Questions on this problem here? Okay. We will end here. Remember, I've got office hours tomorrow, recitation Friday, and then exam also on Friday.